Okay, let's start. We are 8:43. So today we have the last day. We have the last panel of the workshop. We will start soon. After that, we have a poster session and we have two more hands-on tutorials. Today's panel is Advanced Wireless Research over AirPow, and we have 5 great experts in wireless. First, I will just maybe let them introduce themselves. So we have Yuchan Liu, Dr. Yuchan Liu, Dr. Brian Floyd, Dr. Ali Gürbüz, Dr. Sevgi Gürbüz. They form the faculty side, and we have Kalyan Sundar from Keysight. So maybe we'll take a minute for about each of you to briefly present yourself, what you do, and then I'll then present some context slides, and then we'll go to panel discussion. So let's start with maybe Brian.
Hello, everyone. I'm Brian Floyd. I'm a professor here in electrical computer engineering. I've been here 15 years. I lead research and teach classes in high-frequency integrated circuits and systems. We do work on things like millimeter wave radios, phased arrays, high-frequency radar and imaging systems, but all at the integrated circuit level primarily. Another fun fact, I have worked at IBM Research prior to NC State, and we did some early work on 60 gig phased arrays and 60 gig radios. Yeah.
Good morning, everybody. My name is Kalyan Sundar. I work at Keysight. Keysight has facilities worldwide, and if you're wondering who Keysight is HP from the original Silicon Valley garage kind of setup. It's the first one. It's HP, and then HP Test and Measurement Division got acquired by Agilent, and Keysight spun off from Agilent in 2014. It's the largest test and measurement company out there, and I have been happy to have been associated with multiple things in Keysight. I have driven R&D for a long time, center of excellence called Edge to Core, which is where all the ORAN happens. I've been associated with ORAN from its inception and continue to be involved in that. I also drive the what we call network access business that encompasses a lot of Keysight products. So I have a little bit of a business perspective as well. And now I'm also responsible for strategy of how to migrate from 5G to 6G. Which is very important as to, what are the technologies that are going to be important as we go from one G to the next G. So hopefully I can share some of the insights and also learn from, the panel here. Thank you for inviting me.
Hello all, good morning. My name is Ali Gürbüz. I'm an associate professor here at ECE, North Carolina State. My area is basically signal processing and machine learning, but with applications on radar, wireless communications, and remote sensing. Basically, I do quite a little bit of radar imaging, like synthetic aperture radar type of things, spectrum coexistence, especially passive sensing, and communication or radar, as well as integrated communication and sensing problems. I also have one dimension on like precision agriculture with UAVs and remote sensing for that area as well.
Okay, thanks. So, morning everyone. I'm Yuchen Liu. I'm currently a new faculty. I'm an assistant professor in computer science department, and my research mainly lies in the intersection of wireless networking and machine intelligence. So basically, first dimension is millimeter wave wireless, digital twins, and open radio access networks. And I also work on the mobile computing, like the UAV-assisted networks and robotic network in different application areas. Also, our lab works in machine learning and large language model in networking domain. This includes like the radio frequency data analytics and how to incorporate the reasoning and explainability into network prediction. And the last thing is we also developed the open source software like digital twin tools, network simulators, and some other open source test bed. Yeah, thanks everyone.
My name is Sevgi Zubeda Gürbüz. I'm an associate professor at NC State University Electrical and Computer Engineering. My main area of expertise is in physics-aware machine learning for cyber-physical human systems, cyber-physical systems in general. I do a lot of work that has to do with just, how do we take raw, low-level radar data and process it towards whatever our sensing objectives are. So obviously in-home, in-lab environments are quite convenient to do testing, do a lot of work indoors with human subjects testing as well. But in the context of AirPow, really what I'm interested in is counter UAV type work. I do work with the Air Force where we're trying to basically defend against drones and also leverage drones for joint sensing communications, cognitive radar, drone-based ground sensing, and of course, defending against these low RCS UAVs who can potentially carry somewhat dangerous payloads. So.
Thank you very much. What I'll do next is I'll go over some slides, maybe less than 10 minutes, hopefully, and give some context. The goal is, I guess, or the panel is try to come up with some ideas and discussions related to how the advanced wireless research can be done in AirPow. What are the areas that we can maybe contribute as AirPow? And I'm not going to go through these in this detail again. We already talked about AirPow in the first day, but just to remember again our capabilities. We have 5 towers, we have drones, we have a channel emulator, we have the sandbox coming up. Actually, the sandbox, we have the Keysight Propsum equipment that we are planning to open to you for access. So there are trade-offs, as you have seen, and especially yesterday. Channel emulator is great, but maybe there may be stability issues. But that we are working on. So we can have Propsum that captures the hardware impairments and so on with different channel models. Then we talked about the areas at the intersection of autonomy and wireless. So these are the areas I think AirPow has a lot of value add compared to other platforms that are focused just on wireless or just on drones. And maybe one thing that you can keep in your mind is we have the second student challenge happening now, the ADAM challenge. So we are planning to do other challenges in the future years. They tend to happen every 2 years. So if you have ideas about what challenge you might be interested, maybe we will do a poll at some point. It will be great to get your feedbacks as well, now that you are familiar with what AirPow can do. These are the, again, the features and list of equipment that we have in AirPow. We have LoRa, we have Keysight RF sensors, Ericsson network, and we have a lot of data sets that you will hear later today. There will be 2 sessions that you will have demonstrations of what data sets we have been collecting and what you can do with them. And if you're interested in other data sets, it will be great to get your feedback as well. If your research requires you to have some sort of data set, we can try to deploy experiments and collect those data sets. And we have an OTIC, ORAN Testing and Integration Center as well, that was again supported by Keysight and NSF funding. Yeah, so that's the left is ChatGPT, the right is what we have, hopefully. So I have more ChatGPT slides coming up. But one of the critical aspects, I think, is this, I guess the goal for research should be, at least in the universities, we should try to feel this value of that. So in industry, there is all these basically products and services that are relatively shorter term. In universities, we have research that are longer term, and but many times they don't get deployed in the real world, and we don't know if they will really work well or not. So there are all these power platforms and programmable test beds that are their main goal is to fill that value of depth. But then there is this problem of, like we talked to several people yesterday, that they were interested in MIMO and beamforming with 64 antennas. We cannot support those yet. So there are certain cutting edge research areas that industry has very specialized equipment, but with USRPs at this and open source platforms, it takes some time to be able to support research that are advanced. So there are these trade-offs that the test beds have today, but we are hopefully progressing. And maybe the last thing to keep in mind before I go to more ChatGPT is there's this hype cycle, Gartner hype cycle that I'm sure all of you are familiar. Gartner is releasing these every year. This one is for emerging technologies. You can see 6G going up there from, this is 2024. There are a couple of other things that you are familiar, artificial general intelligence, autonomous agents, and so on. So where should we do research, especially with AirPower? So are we, I don't think we are, when something is on the hype cycle, it is more difficult to support than testbed platforms like AirPower because they tend to have very advanced features. So it takes time to develop open source platforms and make them robust enough so that we support research projects that are at the forefront of like 6G, let's say. So I'll just, I mean, these are the ChatGPT slides that are coming up that I was referring. I was asking what are the top research areas and to ChatGPT related to 6G, 5G, and a couple of other areas, and asking it to also assign a percentage of importance. So what do you think would be for 6G? What are the top research areas? I'm just trying to provoke maybe some ideas for later discussion. What do you think is it came up with? Okay, for high frequencies maybe, like the, okay. Any other ideas? For okay, so that are the obvious ones, right? Isaac, higher frequencies. What else? So I'll just maybe just reveal, okay, this is a bit distorted from yesterday. But yes, I wasn't expecting terahertz to be at the top, but it's according to this AI, that's the most hot research area. I mean, I don't agree with, I mean, these are not necessarily, we have to agree. But then AI/ML for AI/ML native networks, Isaac, integrated sensing and communications, NTN, RIS, and network architecture, and then semantic communication. So this is probably not surprising. So these are all areas if you go. Yeah. So it's maybe it was trained by the NSF's website, but so from Wines, but but I wasn't expecting to be terahertz. Maybe some of you, I don't know, are working on it, but with the experience in 5G, probably it's not going to pick up a lot, except maybe for fixed wireless. And then I asked for 5G. 5G is obviously pretty much deployed. But there are still areas. So I was referring to the hype cycle, right? So there is still research to be done in 5G, but maybe not as cutting edge. So these are what came up: massive MIMO and beamforming, millimeter wave, network slicing, URLLC, and massive IoT. So this is also probably not surprising. But these are all examples of types of research we can hopefully support in AirPower. Maybe for millimeter wave, we didn't open it yet, but maybe we can have some discussion with Dr. Floyd on what we have and what we might possibly open with Sivers phased arrays in the future. And then I asked about how about communications and sensing with UAVs. This is what ChatGPT provided: UAV-assisted wireless communications, channel modeling, and air-to-ground channel modeling and connectivity. Isaac came up again. Autonomous swarms and security and safety critical communications. Then we have experts on O-RAN and spectrum. I asked specifically for O-RAN, XAP design and intelligence placement, RIC architectures and interfaces, O-RAN security and trustworthiness, interoperability and integration with RAN 5G, 6G, and then RAN virtualization. And finally, I asked about spectrum. I think this is a big deal. I mean, spectrum always has been a big deal, but especially in the past years, if you are following the national spectrum strategy, US is looking into opening more and more bands. There are 5 bands that are identified now that are going to be open for sharing with maybe 5G and 6G technologies. Dynamic spectrum sharing, spectrum sensing and localization, spectrum policy and economics, terahertz and millimeter wave spectrum propagation, and then AI/ML for spectrum management. And then these are 25 different research areas. I just dumped all of those, and then I asked which of those are suitable for researching, more suitable for researching with AirPow. And Isaac came at the top. UAV-assisted communications, air-to-ground channel modeling and connectivity, XAP RF design and intelligence placement, and then dynamic spectrum sharing. So at this, as far as ChatGPT thinks, these are the areas that are fitting. So just again to provoke some ideas. And first, based on this context, I would want to go to the panel and have some initial questions, and then they will come up here, and then they will present their slides, and then we will have open discussion. So I'd like to start with Dr. Yuchen Liu. Can you comment how AirPow can be used for network digital twins? I mean, you have a lot of research in digital twins to simulate and predict future 6G network behavior, and why it's a unique platform for this kind of research.
It works. Okay. Thanks for asking this question. And yeah, recently we are doing some research in digital twins, and also we incorporate some digital twin tools using AirPow platform, and it's collected data. So basically, I think AirPow is well suited for developing network digital twins because it can serve both as a data sources and as a validation platform. So this enables the closed loop coordination across data system and AI machine learning model levels. Specifically, for example, from the perspective of data level, we know AirPow collect multimodal data from diverse sources, including like the channel radio data and mobility traces, and some high layer protocol configurations, as well as software defined control log information, and 3D network KPIs. So these data are essential to construct digital twins for accurate construction, development. And the second, from the system level perspective, we know AirPow supports disaggregated and software-defined architecture. It is supporting like the open radio access network interfaces, which easily allows synchronized experimentation for multi-layer digital twin instances, such as RAN node twins, user behavior twins, and slice level digital twins. So this is going to support like interconnected and network digital twins, not just a single digital twin for, one size fits all digital twin for a specific network. And the last thing is from perspective of AI and machine learning models. We know AirPow supports the testing for different can support the different AI machine learning techniques, like the classical machine learning models and deep learning, and as well as reinforcement learning. For example, we can train the agent in both AirPow virtual development environment, as well as the real test bed, so we can use real world measurements to construct the digital twin, because AI machine learning techniques are essential techniques to develop the accurate digital twin. So in summary, I think it's a unique platform So in this way, digital twin is not just a replica. It's not just a static replica, but it's a dynamic model which can be continuously updated, synchronized, and be fine-tuned to support more new and emerging network operations and tasks. This is also one of the visions, 6G vision, which is about closed-loop autonomy across distributed and multimodal network environments. Okay, thanks.
Thank you. Let's go to Dr. Floyd next. So you have a lot of work in especially millimeter wave circuits and hardware. What are the hardware research opportunities inspired by air power?
Yeah, so one of my dreams, I think, for AirPaw would be to have a bring your own hardware capability that we could bridge the gap. I think Ishmael was talking a little bit about that gap. But this is really hard to do, to be able to take research from my domain, maybe at a circuit level, and then deploy it onto the drone. But it's still something we're thinking about. But what we are doing is trying to look at new architectures for phased arrays that are applicable to the UAV use case. And then also new architectures for software-defined radios. And I'll have some slides to share about that in a little bit. But kind of a universal software-defined radio. I know that's probably a loaded phrase, but it would be something that could support from low frequencies all the way up into the 50, 60 gigahertz range in a single form factor. I think that could open up a lot of new experiments, and that could lead to other, research ideas.
Thank you very much. Let's go to Dr. Ali Gürbüz. You have worked on integrated sensing and communications. Is ISAC really possible for 6G? We actually had a colloquial speaker earlier this spring. So there was discussion that you need dedicated waveforms for sensing and for communications. Otherwise, you have performance loss in both. What are your views on that?
Thank you very much. Definitely, I think we should start with defining ISAC a little bit more better in terms of when we say ISAC possible in 6G, right? Because ISAC generally, in research community, when we talk about it, covers all the topics where radar or communication can be done together, in sometimes spectrum sharing wise as well. But if we are referring to basically a single system being able to do both communication and sensing functionalities with the same waveform type of thing, then I would say perhaps like the short answer, yes, it is possible, but we should definitely constrain the applications and performance limitations to both of them. Because it is correct that if you are specifically looking into having the radar functionalities, if you have the dedicated waveforms and the only metrics that we are looking in, let's say, radar, is not just probability of detection or the signal-to-noise ratio. There are many other metrics that you might be interested in terms of resolutions, Doppler unambiguous ranges, coupling between range and Doppler, etc. Like that, there might be many other things, or clutter rejections. There might be many metrics in addition to signal-to-noise ratio that you might be looking into, and that might be a dedicated waveform for that. As well as communications, you might have your perfect waveforms for communications that will optimize those metrics, right? So if you are looking the best performance that you might want to get from each of the system, a single thing might not be really, or you might be accepting that it will not really cover give you the best performance both in communications and radar. But if you are limiting your performances to specific applications, let's say an indoor scenario where you might be having like better sensing capabilities so that you might increase your performance in communications, yes, it is possible that you might be doing this with a single waveform, and you are optimizing. But also there are other things. I mean, Brian talking about phase arrays, right? So we are not really limited to basically dividing both these systems in time only. We might be dividing the arrays. So, for example, some part of the array might be doing some communication functionality. Some part of the array might be doing, let's say, radar functionality. You might have cognition between these two as well. So there are many problems in terms of interference rejections or other things between these two. But if you are not expecting to find ballistic missiles from a communication system as a radar functionality, I think, and if you constrain your applications, I said it is definitely possible, and we are going there, I think.
Thank you very much. Let's go to our industry panelists. You have a lot of work especially in ORAN, and you know the big picture on what are the emerging trends. So can you talk about how will ORAN affect 6G wireless networks?
Sure, thank you. So ORAN is here to stay, and after a few years of struggle, I should say, and the reason for the struggle is because you're really opening up the network to many players and some niche players coming in. So it's a very revolutionary concept that was put in place, and we've been working through how to bring that to fruition. So some of the activities that are going on are really interoperability between radio vendors and the baseband units. That's called the front haul, and that's maturing. We have a lot of activity going on thanks to NTIA funding. We were able to set up a couple of labs in UT Dallas and Virginia Tech. This was AT&T and Verizon Accord Consortium. So we are the middleman. We actually look at bringing on board vendor A and vendor B, and we have done a few of these pairings. So, there's a lot of activity that has gone on over the last 1 year. We have just hit the 1 year window now, and we are able to not only make sure things are interoperable, but we are also looking at how can you get higher performance through this, methodology that we are putting in place. Sorry, that's my phone. Yeah, that's fine. So ORAN is, it's very important because it's going to be staying in place for 6G as you move forward. There is another piece of ORAN that's starting to mature, and that has tentacles in multiple areas, which is the whole SMO, RAPs, I would say. XAPs, a little bit less because the opening up of the E2 interface is going to be a bit more challenging. And right now the focus is more on the SMO, which is a service managed orchestration, and the combination of that with the, you can call it the RAP platform. And why this is relevant, and it's just starting to take more shape now, is because you want that intelligence of what to do in a network, not just residing in the base station, but somebody who is a little bit outside of the base station, because they can see what's happening with the different, across the network, from core to the radio to all the different components within the network. So it's a very important thing that's happening there. AI/ML will play a very large role in this. It's already starting to. Here, Dr. Yuchin, you said, yeah, he was talking about network digital twin. That comes into play there because you got to really look at the before and after picture. And we have done several experiments with the companies out there, as well as, these are opportunities that we can also look at here with AirPaw as to how do you do, save energy. It's one of the classic use cases. How do you load a cell at the right levels? Because every time you light up a cell, you actually, there's a lot of money involved there. The OpEx dollars are very high, and operators who are at the top of the food chain are always looking at how do you minimize the cost of running a network. That's the holy grail. So if you can save 10%, which sounds like not high, but if you can save 10%, in the OpEx, that's a big deal. That's bottom line to the operators. They can invest in more things. So this is something that will also be, ORAN would play a big part there. So I think these two elements, of course, the virtualization of several parts of the network is already happening. That'll continue to happen. But that'll be more like an infrastructure kind of thing where you're really not tied to purpose-built hardware where you don't have to be. So these things will carry over into 6G. And there is also another intersection point between ORAN and NTN that's starting to come up. As NTN is taking more shape, there's definitely a lot of clout behind NTN given the companies that are going after it. And the NTN, the primary reasoning for that is how do I get 100% coverage? You've got to be 80%. How do I get to 100%? And if you can get to 100%, you need something like satellite out there. And in the satellite, are you going to put the complete base station? Are you going to put pieces there, like the DU there and the CU on the ground? So there's several architectures being discussed. It is a pretty hot area. A lot of companies are pursuing it as we speak because there's also a lot of satellite operators that are coming into play there. It's not the traditional operators. So anytime you have more players, there is more opportunity for research. There is more opportunity for players like us in the test and measurement side, and that's what we look for. So that's just my quick rundown on ORAN and how it can take us to 6G.
Thank you. That's great comments. So finally, let's go to Dr. Sevgi Gürbüz. You have a lot of work related to radars, and in the context of air power, I guess this maps to detecting and classifying and tracking UAS. Can you comment on your views? What are the challenges and opportunities?
Yeah, so I think, when you talk detection and as well as recognition, the most important thing is signal to noise ratio. And you make assumptions about what the backscatter of the environment is when you try to implement these algorithms. In order to be able to improve all of these, you need to really have like a high fidelity RF simulation and modeling capability that allows you to be able to pursue this. And so I think there's some ongoing work with AirPow in the context of digital twins, which due to the efforts of trying to do RF simulation and modeling, has kind of a natural synergy, which has a positive impact in this domain. But beyond just these kinds of practical matters, there's also challenges that come around due to machine learning, as well as to even how we try to structure and frame the problem. So traditionally, when you think of UAV detection and recognition, you think static radar on the ground trying to detect something flying up ahead. But the reality is that everything is becoming increasingly mobile. And because the detection range of a single radar is so limited due to SNR, if you have the opportunity to have a mobile network which can cover a larger surface, and again, this is like AirPow, it's not originally designed, of course, for counter UAS, but you have an infrastructure there, and along the lines of Isaac, where you're trying to do joint sensing and communications, there's also operational models which can be developed for joint sensing and communications. Oftentimes when you're talking about also DoD applications in potentially hostile operational environments, you don't want to transmit an active system, an active radar signal. So there's a lot of interest in trying to see how we can leverage existing communication systems and signals for the purposes of sensing, especially passive sensing, not just passive sensing of ground targets, but also a situation where you might have something like AirPow, where AirPow is now trying to detect other drones as well. So I think the infrastructure that's being provided by AirPow really has some exciting opportunities in terms of how it could be leveraged as really a test bed for some of these, ground and airborne sensing problems and challenges that we have.
Thank you so much. So next, let's go maybe based on these initial remarks, let's get more detailed views from the speakers through their slides. Maybe we can start with Dr. Yuchen Liu. Can you help for moving to other slides? Yeah, we'll get you here.
Sure. Okay, it works. Okay, so here I just want to briefly talk about some research directions that we are recently working on. So it's about using like LPOP platform and AI machine learning techniques for 6G, Open RAN, and digital twin research. Okay. So the first direction, as I mentioned, we are going to enable like 6G with resilience. I mean, in 6G actually we not only talk about the high throughput, low latency, but also the reliability, right? So it's about how to build a resilient 6G cellular network system. So actually resilience and connectivity are not isolated concept, but they will help each other. For example, improve the connectivity quality can establish the stable link between the users and radio units. And on the other hand, if we build a resilient system, like we can timely handle like different disruptions under like mobility interference and blockages. In this way, we can say we have a resilient system, so we can maintain a stable connectivity among users and different kinds of radio units. So this figure shows the left part shows some evaluation result based on our recent research. Like it's a 2D dimension. If we deploy our radio units in a 2D plane, like in a confined places, like we deploy the base station, small cell base stations on the roof of the building or on the surface of the building, we see it can achieve a good average user throughput and the load balancing among the radio units. But in worst case, I mean, under disruptions like blockages, interference, sometimes the user throughput may go to the zero, right? And but if we go to the 3 dimension, and we say if we deploy some mobile, I mean flying base station like UAVs, it improves the flexibility to deploy these radio units not in a confined 2D space. And in this way, we say we can maintain a stable user throughput, but also we can improve the worst case scenario, to counter the different disruptions under blockages and interference. And also we can achieve the better system load balancing among the radio units. So in this direction, our recent work developed some resilience aware framework. So like the first step, we generate some scenario configurations like in different urban scenarios, and this can also use collected data from the LPOP platform. And then we have a resilience quantifier, like we keep monitoring the resilience of the network system. So once we find the resilience score is below a threshold, we can try to reconfigure the network topology or reconfigure the protocol. Do the protocol reconfiguration, or we can move, maybe if we have the UAV, the radio units, we can stretch the topology to overcome the interference or blockage under mobility and other kind of disruptions. So this is also based on the reinforcement learning mechanism, which can train an agent to adaptively maximize both user coverage and balance the traffic load among the radio units we use in the environment. Okay. And the second direction, to enable the Open RAN with air mobility, actually we envision some scenarios. Like scenario 1, we envision that definitely UAV can serve as the users, which collects the first-hand data, environment data, and radio data, and send them to maybe the radio units, and then to the near real-time rig, which can make the timely decision for different network operations. And scenario 2 is we can deploy the UAV, maybe serve as a central unit or distributed unit to like in scenario 3 to achieve the RLC, MAC layer, or higher physical layer functionalities. And scenario 4 is like we can form a drone swarm based open radio access network with UAV, so they can quickly form a aerial networks for critical, mission critical network tasks. And scenario 5 and 6 is like UAV can serve as a relays for backhauling from the cell base station and the core network, and also support the D2D, the SAT-link communication. Okay. And the last direction is I just mentioned is about the network digital twins. So one difference between digital twin and network digital twin is sometimes, network is the current network infrastructure and system is a very complex system. So sometimes it's hard to build a one-size-fits-all digital twin for different kinds of network requirements. But here we try to build several multiple task-oriented digital twins, and these digital twin models are connected with each other. So this form a network, the digital twin. Once we have a request or new requirement, we can trigger like one or more digital twins, and they can collaboratively achieve the new functionalities, self-adaptation to fulfill the user's requirements, to improve the network performance, etc. So in this direction, we actually build some digital twin tools based on like the Siona ray tracer, and in this ray tracer we can we can actually generate the very high fidelity urban environment with details like buildings, streets, and then we can modeling how UAV and user communication behavior in this complex environment. So basically, when UAV move around, we can monitor the user throughput, like the system load performance and the UAV energy consumption in this virtual environment. And also, we are going to, like, if it's possible, to incorporate this kind of functionality in LPOL virtual development environment, because previously we attended the first LPOL challenge. We know we can use the LPOL virtual development environment to simulate many the UAV, like the fan, to fan the rover using the radio signals, and then validates in the LPOL platform using the real world signaling data. So this is one thing. Maybe we can combine some existing ray tracer with the LPOL platform. And also recently we also developed the new functionality in NVIDIA Omniverse digital twin tools for infrastructure planning, and also it's possible like to use the Omniverse software tool to generate like the scene configuration files and export this data format to maybe to the LPOL virtual development environment, and then we can simulate many what-if analysis, like different scenarios, and finally validate in LPOL platform with a real-world signaling data. Yeah, and that's all for my presentation. Thank you, Chris.
Next up, we can have Dr. Floyd.
All right, so as I mentioned, my team, we do work in integrated circuits and systems. I made a little collage here to show what that looks like. A lot of our work involves building actual circuits, getting them fabricated, measuring them in our lab. And then some of the work involves the next level up, where we'll take the hardware, work with digital platforms, and test them at a system level. And this includes work at AirPaw. And so on the upper left is a shot of the millimeter wave capability that our team was looking into deploying into AirPaw. And at the outset, when we originally won the award, this is one of the capabilities we wanted to provide, a 28 gig phased array. And one of the goals was coming up with a software-defined array that also is affordable. And so we came up with, identified the solutions, and this included a commercial off-the-shelf phased array from Sievers Semiconductor, 16 element, 28 gig, paired with a Xilinx baseband that can support up to gigahertz type bandwidths. Now we are still working to figure out how to get this deployed into the system, and we'll probably still be sending out user surveys, and you all can comment on how this might be useful or not. Some of the ideas that we have in mind obviously are looking at millimeter wave communication links and radar capabilities, as we heard earlier. Another one was looking at out-of-band emissions. And so on the lower left, you see a map of it's called the brightness temperature observed from space looking down at the Earth, and at 24 gigahertz. And so these are essentially used in weather prediction systems, and what they're monitoring is water vapor in the atmosphere. And there's been a lot of concern of 5G millimeter wave impacting or cluttering, I guess, this capability due to out-of-band emissions. And so one of the things we hope to be able to do is measure out-of-band emissions from a 28 gig phased array down at 24. And then I think we have interesting ideas from a hardware level of how to suppress that, depending on that level. Now, on the upper right is a view of, I mentioned universal software-defined radios, 5 to 50 gig. And that's not just a fiction. If I were to, sorry, there's an animation that's going to distract you. Resist the urge to look at that animation and look at the upper left. This is a screen, a plot showing one of our hardware that we've built and measured. This is a tunable filter that tunes from 10 to 40 gig in one circuit. And the bandwidth is roughly 1.5 gig. This is by design. We have other designs that can be tunable bandwidths from 100 meg out to multiple gig. Tunable filters kind of like a holy grail in the circuits domain, and there's a graveyard full of failed designs. But we think this has some opportunity for us. Now, it's not as good as a passive filter, but there are certain applications at which we think this could be really helpful. Now, on the lower left, you heard some comments on ISAC or JCAS. People need to get together and pick one acronym, but sensing and communication. And we're doing some work at millimeter wave, and what's interesting at the millimeter wave side is if you want to do in-band full duplex, that means transmit and receive same time, same frequency, you have a self-interference problem. What's interesting at millimeter wave in the architecture side is you can put that self-interference cancellation at different points. And so you can steer the antenna pattern to give some level of rejection. But here we have been investigating what we refer to as subarray interference cancellation. So between the front ends that have the phase shifters and whatnot and the rest of the radio is a natural point to do that cancellation. I'm trying to keep us, yeah, and so then on the upper right, to finish things out on that right side, we have a lot of research in my group on different types of phased array architectures. And so this is an example of an array we built for a satellite communication array. So it had different objectives, need to be scalable to up towards thousands of elements to support the link budget. This is a transmit, and so it's for the uplink operating around 40 42 gig. Now what you're seeing there are waveforms that look very tightly clustered, and that's the goal, right? And so we are showing, as we program the phase on the right, that the amplitude on the left is not varying. And so we have research not only on the circuit level, but also on the algorithmic level, how to do that calibration better and better. And then that finally, you can now look at that animation. What that animation is showing is just a simple optimization script. And we've used Bayesian optimization in circuit contexts for phased arrays and for radio. And we're just about to start a new program looking at AI design of RF power amplifiers with Keysight. Keysight's the prime, and then there are a number of partners. And the idea, I think at the end of the day, it's not going to be like compile the PA, spits it out, and it comes back. It's more going to be a co-pilot for designers. And so as we have co-pilots that help us write, or as help us, Ishmael, come up with nice slides, we will have a co-pilot that help us come up with better circuits. And so we're looking at that. So I'll stop there. So thanks.
And have Dr. Ali Gürbüz next up.
Okay, thank you very much. Okay, that's great. Okay, so I will talk a little bit, basically, briefly about one or two basically problems that we are looking into, and how we can really use air power in these problems. One of the projects we have is related to passive sensing and active communication coexistence. Brian showed you some brightness temperatures at 24 gigahertz of the whole world, right? Basically, every object has some temperature, and if you have seen like some thermal cameras, you might see yourself kind of at a different temperature or the background, right? So basically everybody is radiating at every frequency, not only thermal infrared frequencies, but even you are basically radiating at, let's say, 24 gigahertz or at different frequencies, at these microwave frequencies as well, but it is so little. And some of those frequencies are basically affected. For example, 24 gigahertz, Brian showed, might be affected with water vapor in atmosphere. At a different frequency, let's say L band, the soil moisture content might be affecting the measurements. And these passive sensors are basically so sensitive receivers that they correct even the noise levels in those circuits so that they can measure these radiated signals from Earth precisely, so that they can convert those measurements back to whatever the remote sensing product at the end is. So communication signals at different frequencies definitely might be altering these. And how to basically coexist, even you are looking into 28 gigahertz affecting a 24 gigahertz, right? I mean, if it is much closer, what might be the effect, and what are the basically some solutions in terms of algorithmic level approaches to detect these type of, let's say, you might call, if you are looking from the perspective of at least these passive receivers, all the communication signals or radar signals as interference to them. So how you detect the interference, how you can mitigate the effect of these interferences, what might be the most kind of acceptable level of transmissions from these systems with the given defined performance changes in these remote sensing systems also. So when you look into all of these, definitely you might need to collect data and really look into effect of these systems, or at least be able to simulate and develop really digital twin type of architectures, right? Collecting data with these systems are not easy because you, for example, in the ranges we looked earlier, such as L-band, you are basically restricted. These systems, you cannot really transmit at these frequencies because the only frequencies, basically these passive systems are saying, okay, only that passive sensor will be working over there, right? So you can just do experiments in anechoic chamber type of things. But we basically developing some data collection structures and scenarios that can really be practical so that you can develop your signal processing or machine learning approaches are highly critical. So in this project, in a previous one, we developed some anechoic chamber experiments, and I will show that. But in this project, we are basically developing a passive remote sensing system, this passive radiometer system at S-band from 3.2 to 3.6, so that we can basically develop some scenarios with the AirPow system over here. For example, we can take AirPow base stations as transmitting scenarios, sorry about that, or like UAVs as transmitters, or ground vehicles as transmitting scenarios, so that we can develop like different kind of geometries for these transmissions, so that your passive receiver might collect data from all these different applications. So we are also developing like digital twin for this passive architecture, so that we can simulate these scenarios in high precision. And the second part of this is definitely developing like signal processing and machine learning approaches for both detecting these interferences and how we really mitigate these. So we are looking into in-band or out-of-band transmissions at different levels and understand the effects basically on the passive receivers. This shows you the experimental test bed for like L-band passive radiometer, and we developed some data analysis and generated a data set for this at different levels. Basically, the very raw IQ level data that the radiometer received. Basically, the important thing for this is what is the actual brightness temperature, the correct brightness temperature, so that you might understand the effect of the interference to the actual output product of this sensing system is important. So here you see this system is the radiometer. You are like generating 5G signals with our software-defined radios, and over here transmitting, and we looked into in-band, out-of-band scenarios. We did this in anechoic chamber because we weren't allowed to transmit at these frequencies outside. But for radiometer system, it will be at 3.2 to 3.6, where we have license at AirPow to do different transmission scenarios. And this data set is publicly available right now. If you are into passive active coexistence type of scenarios, this is an actual real radiometer data set that you might look into in terms of developing RFI detection and mitigation type of structures. In terms of these RFI detection and mitigation, basically we are looking into many signal processing and machine learning approaches, but one of the main things is really in analysis in time frequency domain. So you might look into basically the time frequency domain. The RFI, or like the communication or radar signals, doesn't cover generally the full time and frequency domain or space, right? So you might have, let's say, different communication signals, or like perhaps a radar signal over here. So one of the problems is kind of detecting if there is RFI here, saying that this time frequency domain has RFI, or if you might do looking into the high resolution time frequency domain RFI detection, where you might really try to locate in time and frequency the specific RFI regions and then try to mitigate it. So we are developing algorithms to do this high resolution RFI detection and mitigate it so that you could really understand or estimate the final brightness temperature that these remote sensing systems are interested. We are looking also in kind of recognizing what type of waveforms, if it is a communication or if it's a radar, what's the modulations in those signals as well as in terms of both communication and waveforms. And there are like machine learning approaches, especially we are developing approaches that can directly work on the raw IQ data without doing time frequency transforms and with less computational complexity, as well as more interpretable architectures so that we could understand what these black box machine learning architectures are actually doing. And some of the additional things that we are currently trying to do and that will have some projection to AirPow or basically test with AirPow is passive sensing structures, especially when we think about passive radars. One of the architectures we might really do is we might have this receiver. This time is not a passive receiver like the radio meters, but like a radar receiver again, but just only listening in, not really transmitting anything. But our AirPower base stations might be transmitting, and you might be getting the direct signal from the base station, but also these will be reflected from targets as well, and you might really do passively detect these systems as well. Localization, basically using signals of opportunity, and those signals of opportunity sources, for example, could be AirPower transmissions, so that we could do localization. As well as one of the problems we were interested is the confliction between UAVs, so that, I mean, one UAV controlled, etc. is good, but if you have multiple UAVs in the same airspace, how can UAVs can sense each other or communicate with each other, so that you might be looking into a deconfliction. And the other problem is definitely detecting these UAVs, but radar is one solution, but as well as other solutions like cameras, acoustic arrays, or passive or communication systems as well. I think that covers what I wanted to say. Thanks a lot.
Thank you. Next up, we can have Kalyan Sundar from Keysight. So we'll probably go over 10 to 15 minutes after 10. We started a bit late, so I want to make sure we have time for discussion and Q&A. I know some of you have poster presentations, but you don't have the boards yet. They are coming soon, so we will have some time. We'll probably start the posters at the end.
No worries. How is everybody doing? Awake? If not, let's wake up. Let's keep it interactive possible. So I think there are many things we can talk about. I just picked one topic here. But before I get to that topic, we briefly touched on O-RAN maturation. Clearly, that maturity curve is, I would say, behind us largely. A lot of key operators, AT&T, Verizon, Vodafone, the Japanese operators, they're all behind it. And like Dr. Ishmael mentioned earlier, whenever there is new spectrum, there is an opportunity for getting new technologies into the fray. When you don't have new spectrum, typically an operator is forced to think about, when do I do the upgrade? Should I, just because it's nice and fancy, should I go to disaggregated networks? What is the benefit it provides me? How much of cost do I incur there, et cetera, et cetera. So about a year and a half ago, AT&T announced that there's a $14 billion contract with Ericsson and a few others. That actually allowed Ericsson to come into O-RAN in a big way. Until then, Ericsson was kind of the monolith sitting outside, along with the bigger vendors like Nokia, Samsung. You know, these are the big three outside of the Chinese vendors. And it's very important because these base stations had the radio, they had the baseband, they had pretty much everything. So the disaggregated concept came in where you're separating the radio out, you have a frontal interface, you're separating out some of the intelligence into applications that are going to be sitting outside of the base station. That's the whole RAP and the SMO and even XApps, which are still, out there for research and other activities. So I think that's the first thing. So this is going to carry on into 6G. ChatGPT was largely right. There's a few things I would probably recalibrate. Is sub-terahertz really going to take off? Probably from a research it will, but already we see that there is diminishing return there. People are looking more at FR3. So if you're focused on what will get deployed faster, it's probably FR3 because it's more likely for operators to pick that up and deploy. Sub-terahertz will still be there in the research, but I think largely from a operational perspective, FR3 is gaining very quick prominence, especially the upper 6, as we call it, 7 to 8.4. A lot of companies are already moving to the 8.4 gigahertz band and so on. So there's some value there. Clearly sensing, a lot was said about it, so that's there. My presentation is largely about AI. I have a couple of slides there, but I'll piggyback on what Dr. Liu was saying because a lot of this actually resonates with me in terms of what we could do overall and how we could move this forward. So the topic I want to pick today is AI RAN. That wasn't largely spoken here. And this is gaining a lot of prominence. AI RAN is, it shot into prominence last year in Mobile World Congress, 2024. AI RAN Alliance was announced. The companies that are behind it are NVIDIA, because they're obviously pushing the GPUs, and there's a lot of possibilities for that kind of computing power that's required if you marry AI with that. So that's one. Clearly, SoftBank was another one that was pushing it, T-Mobile. So two big operators, and then Ericsson is in the fray as well. So there's some companies, and now it's about 85 members that are part of the AI RAN Alliance. And there are three aspects to AI RAN. The one that's immediate is AI for RAN. And AI for RAN is basically how do you use AI ML to improve the spectrum energy efficiency and few of the use cases that are called ORAN or RIC use cases. And where this place in, there's a place for it, and I'm going to go through an approach that might make more sense. And I'll also try to draw a parallel with the UAV because that is one of the ways you could input into this whole system. So AI for RAN is immediate, imminent. It's already starting to gain a lot of momentum with the in the corporate world, right? The second one is AI and RAN. When I want to run both the AI workloads with the RAN workloads on the same equipment, again, virtualization is an important factor here. You're talking about a lot of network infrastructure for AI is going in today. If you look at, ASML, TSMC, there's just a lot of value that's going on into that and a lot of NVIDIA-based purchases and opportunities that are going in. I don't know if you read this, but OpenAI is going to lease, a data center from Oracle. It's a $40 billion purchase that Oracle is making of NVIDIA chips, and they're going to lease it. It's a data center in Texas. It's going to be leased to OpenAI. So there's just a lot of need for computing power. There's a lot of need for chipsets and GPUs and so on. So there's just a lot of value. And here you're looking at how do you maximize not only running AI workloads, but also can I use it for RAN? So that's the whole premise between the AI and RAN. It's going to come a little bit after the AI for RAN, but research is already going on in this space. Last is AI on RAN, where how can you come up with new AI-based applications and services in the wireless networks? Still to be defined, there's still a lot of interest. This is going to be a research activity. But if you look at it, these three pillars for AI, RAN is going to shoot more into prominence. In fact, I think the value chain will start moving more, if I would say, from ORAN Alliance into AI RAN Alliance. You're seeing more and more of that. So just keep that in mind. And what I want to do with this is I want to just focus on AI for RAN in this presentation and see what that means overall. So there are again, Keysight supports many use cases, but the point here is there are three alliances or standards bodies that are behind it. There is, study items on release 19 that some of you may be familiar with. How does AI/ML affect the NR air interface? That's the RAN1 group. There's also one for 5G NR mobility. These are things that Keysight participates in. There is also ORAN Alliance that is looking at AI/ML workflow definitions. And the AI for RAN, like I was mentioning, there are experiments that are going on, like, receiver optimizations and so on, where I can drop in a different receiver than what's in the chain and see what kind of benefits you get. Sensing, of course, is also very much part of that. So there are several use cases here. The ones in green are the ones we are looking at for the RIC and SMO-based technologies, how these use cases like mobility management, fault detection, prediction. Again, some of these have been in place from SON days, right? Self-organized networks, but it's getting to be more real. There is more opportunity. And again, wherever costs can be saved by operators, you're going to see more momentum coming in because, again, they're at the top of the food chain. If they spend, it trickles down to every aspect of the system. Of course, the government like NTIA is doing a lot of good stuff, NSF, grants and those, but there's also interest in terms of how do you make this real. NTIA has spent, in the NO4 1 and 2 and now NO4 3, there's just a lot of dollars they're pumping in. Not just US government, you're seeing it in Japan, you're seeing it in parts of Europe also, and that's very important because that's the infusion that's going to be required for some of these technologies to at least get incubated so they can be brought into force a bit later. As you all know, research has to lead the way, then comes the industry. But you're trying to couple what would industry benefit from these research. There's a tighter coupling now that we see. So what is the AI for RAN workflow, right? So we talked about the creating data sets for AI/ML. So UAV, Dr. Liu talked about how you can have UAV gather data. And that's the first pillar or the top, leg of the stool, as I call it. It's a three-leg stool here. The first leg is, data set generation. And data set generation can be done in so many ways. You can create synthetic data through lab experiments. You can pull that out. You can get operator data from asking the operator, can you give me data? But think about it, right? The data is so large for an operator. First, it's also very sensitive. It's not easy to get operator data. But even if you get the operator data, it's going to be at an instant of time. And that's could be representative of only that instant of time. But if you want to normalize data over a 24-hour period or over a weekend, whatever, you need to take the data and do something with it. You can't just say, give me all the data. That's not going to work. But you want the seed data to come in from operator. It could be from UAV. It could be from anything. In fact, we did an experiment, Dr. Liu, just to go back to some of the things he was talking about. And we demonstrated this in Mobile World Congress, where we have an R&D facility in Malaga, Spain. And in the downtown, we had some drones flying and capturing the patterns of what's going on, the traffic and so on. And we were able to map it and create a channel out of it, take the channel, put it into our PropSyn, the one that you have here, and we were able to make some modifications, add channel modeling, so we could really take that channel and do a lot of things with that. And that actually feeds into the digital twin. That feeds into the digital twin because you need, again, an accurate representation or close enough approximation of what the reality is. And there are many ways to create that. So that's what I'm pointing to, that first leg. And this is of prime interest out there. How do you create data that's meaningful, realistic, and that can scale? So you take that, and then you move it into the AI/ML training phase, which is two things. One is data scaling. You take the data, and you need to scale it over a longer period of time, number one. You want to look at diversity of the data, because it can be what we just captured in NC State. Is that reflective of US traffic? How do you, apply some intelligence to that? So we're going to look at the data generation phase, and it's all about data at this point. You're not looking at the domain, you're not looking at anything, it's pure data modeling. So data engineers, we can have data engineers go look at the data, see how they can make the data diverse, how you can add security to it. So there's a whole pipeline of things we do there. That's the second phase called AI/ML training. Then you look at the domain. I want to apply it to energy efficiency. So there, do I really need a lot of data? Do I need specifically some types of data? Or I want to create some, PCI collision, or I want to steer traffic from one cell to other. How do I do it? What are the conditions I do it in? That's where you create the model. And when we do the model, that is where the domain expertise comes in, where, you want to apply both the domain knowledge as well as AI ML there and create this model. Now you want to take this model in the last phase, you're actually running it against a target. You're running it against a target, and now does it make sense? What you're getting out of it, is it really reflective of what you want? Can you explain the results first? And can you take that and benchmark different vendors out there? I want to take Nokia, I want to take Ericsson, I want to take different operators. Can I benchmark and give a score saying you did better than that? It's more like your speed test. You could do a speed test, but you could do it at this scale. So can you explain what the data is? And then it's a loop, right? You refine, you take that model, you make the changes, you go into this loop. This is what you do. So I think this three-legged stool is very reflective of, first of all, how to gather data, how to refine the data, and how to make sure this data is very valid and as close approximation as possible. Now, if we can do this successfully, this can feed into most of the use cases that the industry is interested in looking at. Because the operators want first very realistic approximation of what's going on. You can use it for planning. I think one of you showed a slide about planning and infrastructure. You could definitely use it for planning networks. You could use for optimization of networks. You could look at how you can save costs, which is a very big deal out there. And that will also feed into, okay, I save costs. Now, can I replenish existing infrastructure with newer equipment, whether it's ORAN, or I want to put more emphasis on NTN. Ultimately, you got to save costs to spend the money somewhere else. That's how it works. So I'll pause there for any questions or anything people may have. But I just wanted to touch on this one subject. 6G is so large. I mean, we can talk for an entire day here. But I wanted to touch on one subject here. So any questions or anything before I hand over the podium?
Last presentation, we'll probably go until 10:20, so maybe I want to have. Dr. Gurgus, do you have any slides or? So we'll
okay, perfect. Thank you.
So there is a saying that I like from a British statistician, George Mark, saying all models are wrong, some models are useful. I don't know if you have heard that. So that's I think that's a great point about the model. So AirPower and platforms, they can help developing more realistic models. There are other papers out there that
should be the one that says Dr.
modeling
Z.
assumptions that are not accurate, so the conclusions will be wrong.
All right, so in the interest of time, I'm going to try to keep this a little bit short. And the way I've structured my talk, instead of giving specific results, is more structured around, I think, core concepts that I want you to think about when we think about how we might be able to think about the sensing problems involving both defending against UAVs as well as doing UAV-based ground sensing. So what is the problem? This doesn't have to be like a consigned unit. This could be somebody's home. This could be a school. This could be any facility where we're concerned with trying to defend against drones, and we're concerned with other types of intruders. Whenever we're trying to do detection, we actually have a two-part problem. It's not just a challenge of, do we have a target detector which tells us that a target is there or not? We also have to understand what the target is. And this is where being able to understand and differentiate from other types of confusers, such as birds, for example, comes into play. You don't want to trigger your system every time a bird flies by your organization. And so we have this two-part problem of detection as well as target recognition, which comes up when you're dealing with both people as well as other types of animals and drones. So what are the approaches and techniques that we use to handle this problem? There was a lot of talk in the previous by the previous speaker and others, which thankfully I'm going to kind of leech off of, because whenever we do, thank you again, whenever we do AI ML, right, he very nicely eloquated how we need to have data. Right? And so data is great. The problem is with sensing is that you can never have enough data, number one. If you actually want to go out and collect sensing data, that means somebody has to fly the drone, or if it's a person, somebody has to go out and walk and give you that data. Number two, it's very practically infeasible to be able to collect data across all scenarios. I mean, think about it. All the different types of operational configurations you can have, all the different environments that you could possibly have. You can't go out and collect it all. That's really not possible. And then number two, given the subset of data that you are able to collect, how much does that statistical distribution actually match, therefore, with the scenario that you're in right now, right? So data is great because it gives you like a temporal snapshot. And if you have a dynamically changing environment, it tells you something about your environment at that particular time. And if you're trying to measure or sense a target, which you haven't actually been able to acquire measurements for before, it can tell you something about your specific target and its properties. And if you have a specific radar system that you're operating, sometimes radars also have hardware-related artifacts. Several years ago, I had a particular software-defined radar, which for whatever reason would throw horizontal lines in the time frequency transform. It was something to do with the hardware. Seriously, we spent a lot of time debugging it, worked with the company, and even the company finally confessed that this was a hardware artifact after a lot of arguing, because it takes a lot of haggling to convince a company that they actually built something that has a flaw in it. Okay, and then as a signal processing engineer, we have to figure out how to clean that up, right? So I don't want to blame the hardware people. You know, they build as best as they can, and then we have to clean it up. That's our job. But my point is that you can have sensor-specific artifacts, which even in your training data is not originally captured. But when you're currently using the system, those problems exist. So data is great, but it has some shortcomings. In my experience, whenever I take data-driven deep learning models and I directly apply it on sensing data, if I just dump it into the black box, it does a lot of crazy things. Like, you know, when I apply this on human data to try to synthesize, I can generate samples where if you physically interpreted the data, it would correspond to a person who was split in half and falling in two directions. Why? Why do deep neural networks do this? Well, because you're using computer vision algorithms which are keyed towards capturing spatial correlations. And if that underlying correlation is not existent in your data, then it makes mistakes. So oftentimes with sensing, especially radar-based sensing, the computed images that we generate for the purposes of target detection and target recognition and tracking, they don't have the same physical spatial correlations as what you would expect in optical imagery, because your X and Y z-axis are not spatial dimensions of X and Y. It might be speed and time, for example, right? So this is where physics-based models become important, not just to generate more data, but to try to generate more accurate data. And for all those scenarios that we couldn't collect data, we have physics-based models that can help us capture those things. But what type of models, right? You can do computational electromagnetics and spend a lot of time and resource to generate really, really high fidelity RF models. But that too takes time, and it introduces complexity. And ultimately, it can't specifically capture the data that you're having at this particular time. So even though the physics-based models embody a high degree of knowledge that can help temper the errors that occur in deep neural networks, again, the question arises of what model do we use, kind of when, how complicated does it really need to be? And unfortunately, I'm very, very lazy, and my laziness has formed the basis of my entire research area, because I don't want to go out and collect a lot of data. And I don't want to collect, you know, do a lot of simulations with like RIF. So I'm in this middle area. I'm trying to do physics-aware AML, which can translate over a lot of different things that we're doing, not just obviously the drone problem, but my research has evolved. How can I design the deep neural network architectures so they're better matched to RF data so that we can easily expose the underlying physics of the data to be able to best use some amount of data, not a lot of data, some amount of data. And we try to get really the sweet spot in terms of performance, computational complexity, real-time performance, accuracy, and all of those good things. So this translates to a lot of different things. And of course, in the drone problem, which I also specifically work on, this becomes essential when you're trying to be able to detect drones in a wide range of signal-to-noise ratios, where you might be in a lot of different environments, sometimes next to trees, sometimes out in an open field, and you would expect that the dynamic properties of the clutter are greatly variable. The other main concept that really kind of now lynches off of what Dr. Floyd was talking about with like the adaptive hardware, like your universal SDR, like I need that now. This is like such wonderful, we need to so I talk here about multifunction, fully adaptive cognitive radar, and that's essentially all the different signal processing tasks you could do given Dr. Floyd's universal software-defined radio. Because essentially, if you take a look at these tasks of detection, localization, tracking, and target recognition, what you find is that actually transmitting just like a fixed waveform across all time and space is not really the optimal thing to do. Depending on what the target is doing, what the dynamics are, what environment you're in, and also what the function of the radar is, whether or not there is interference, whether or not you do have to account for missing data or certain bands that are now being overlapped, actually the optimal signal that you would want to transmit from the radar can change. And a good example I can give you this is even something as basic as target tracking, for example. It can be shown that if you variably adapt the pulse repetition frequency of a radar, that you can get significantly better tracking performance over time, right? And so this idea of fully adaptive radar is basically the idea that you're not just going to change how you're processing the signals based on what's going on with the clutter environment. So like the physics of AI/ML, that's all on the processing side. But we also want to change what we're transmitting so that we're transmitting the right thing at the right time for the best performance. That would be like the really top level conceptual way of framing this. And this becomes important for a lot of different tasks. I've shown here this framework within the concept of a cyber-physical system because I think this relates to any type of autonomous system that you might be trying to control, and it also relates to any kind of sensing problem. So you can see applications of this not just to air-power problems, but you can see applications of this to human-vehicle interaction, to any kind of human motion, gesture, body language, remote health monitoring, whatever kind of sensing problem and context you have. We've seen that being able to apply this gives distinct benefits. At the very least, also, think about the fact that when you're trying to process radar data, that the complexity and the dimensionality of the data does depend on the waveform. So if you transmit something very rapidly with a high bandwidth, you're getting a lot more data now that you have to process for a machine learning algorithm. So especially when you're working on real-time problems, this issue of how can you do the trade-off between computational complexity and real-time performance, adapting your transmit waveform helps you balance that. Don't transmit something if you're not going to use the data, for example, at the very least. So again, like so many other speakers, we can talk on this like forever, but these were really the main 2 points and thrusts of my research I wanted to touch upon. So I only have 3 slides, unfortunately. But again, I look forward to your comments, questions, and to discussions afterwards. Thanks very much.
Very much. So we started about maybe 15 minutes late. Is it okay to start the poster maybe 10:45 or so? And is the panel good to go till maybe 10:30? We take another 20 minutes. Do you have any commitments? Yeah, we'll have a shorter break, maybe. Posters after lunch. Posters after lunch? Oh, okay. I confused the sessions. So we'll start yeah.
So we can start the short break a little.
Yeah. All right. So I just want to make sure we have a great panel here. I somehow miscalculated the timing, so let's take about maybe 20 minutes or so for Q&A. I had my questions, but I'll skip them. So any questions for the great panel from the audience? Giving the microphone, maybe you can.
Right. So most of the ones covered the one widely talked about terahertz and NTN, ISC, and or AI/ML, all those ones when it comes to 6G. My question is, what is the possibility of new waveform for 6G? I know there are a lot of research work going on, like OTFS and other ones. That one. So just want to get an view on that. Do you see a possibility of new waveform when it comes to 6G?
Asokan, we have seen, I know Asokan from the past because we used to be colleagues, so that's why. No, we we do come across OTFS. I think there is a push for that. It's too early to say. I think in some ways the hope is 5G. Actually, don't know what it exactly stands for. I can look it up. If you can Google it and tell me exactly what it is. Okay. So it's being pushed by Cohere Technologies. They are in the forefront of that. And I think there are still some. I think basically the 5G in some ways, depending on who you talk to, hasn't really taken off. Okay, irrespective of what, there's obviously people who are really in favor. Compared to 4G, 5G, the killer use case didn't happen. And if you look at 5G, the original promise was enhance mobile broadband, the massive IoT, and low latency URLLC. URLLC and massive IoT hasn't taken off yet. So those are going to come in some form in 6G. There's always a need for more bandwidth, and EMBB definitely was one of the drivers. There's also allied things like SA core that still are happening. So I think to come back to your question, there is opportunity for experimentation, but is there going to be radical changes? I think most people don't want that. They want to see how they can 5G as a launching pad and get 6G, some of these things in. It's too early to call whether it'll be out or not. Obviously, there's discussions, but that's what we believe, that some of the, that's why even sub-terahertz, very quickly there is a momentum to not really go too far with it, based on what we saw with millimeter wave. So millimeter wave didn't take off, then what's the chance of sub-terahertz taking off? Maybe the niche application somewhere. So I think operators are also more savvy now. That's why FR3 is gaining strong ground. So they're looking at technologies that can quickly propel them into making 6G a success early on. At least that's today's stance. We still have 2-3 years before that can change.
I have two questions there. The mic.
I have a question for Sevgi about relating to sensing systems on like drones. So I have a little bit of experience with millimeter wave radar, and I'm kind of interested in what the challenges may be for sensing and identification when the radar itself is moving.
Yeah, that's a great question. Thank you for the question. I think the biggest problem is just the fact that you're going to get vibrations and other types of artifacts due to the platform motion, which if you had a stationary radar, you would assume that all of those movements you would assume have to do with the target. But now when you're on a moving platform where maybe, again, this is where localization becomes so key, but, how do you account for maybe these really like high frequency fluctuations? I highly doubt that filtering is going to be adequate. When you try to do any kind of imaging like synthetic aperture radar, you have to account for all of these types of phase shifts when you're coherently trying to account for the signals. So there has been a lot of work on, like, for example, SAR-based drones, which has some success. There's also been some work on like drone-based vital sign monitoring. Actually, just a few weeks ago, I had a conversation with a guy who works in that area. And the problem is, how do you do this reliably? Like, you can do drone-based, for example, vital sign monitoring with radar, but it doesn't work on all of the samples you collect. It works on some of the samples you collect. So again, how do you just deal with the drone motion in all of your algorithms so that you get robust performance?
Has there been any research into maybe transformations on the basis of inertial data from the drone?
So I think the biggest issue with inertial data, and that is used in like SAR reconstruction, but usually that type of GPS data is not sufficient to kind of perfectly focus the image. You still need to use electronic autofocusing techniques. So yes, inertial data is used, but it's not adequate. You need other things to actually get the pulses to coherently sum.
My question is Keysight. What was your name again? Sorry. Kaliat. So I'm all about mesh networking. the topology right on its face looks attractive, but making the nodes think hard enough to dynamically route the traffic, a lot of people say it's just not there yet. I see it more as like more of a redundant layer. But with the introduction with like 6G and using AI and ML, do you see mesh networking, or is there any conversations of it being more integrated and reintroduced into the environment in today's day and age?
I'm not too familiar with that topic, honestly, but I do know that disaggregated networks is coming into play. That's not exactly mesh networks, I know, but that's all I can say at this time.
No one has questions? Yeah, we have slides.
Yeah, so just generally, I mean, there are many technologies in 6G that we're speaking about, but what's like concretely coming? What do you see like vendors are pushing towards, and in let's say a 3GPP standardization?
It's still very early days, so I'll caution us that things will change. But there was a forum in Korea, the first 3GPP session. I don't know if some of you attended that from here or not. We did have a couple of representatives from our company, and the feedback we got was clearly AI ML. There is a lot of interest. Again, this is propelled by the general AI ML. I wouldn't call it a hype anymore, but let's say hype for the purposes of this. So there's definitely a AI ML aura around the whole thing, let's say. Using AI ML and how we can gain more effectiveness, etc. That's one topic. Sensing definitely is also moving up. Always interest in FR3s definitely was discussed in the corridors and everywhere. So I think if you look at that forum in Korea, these are some of the things that propelled forward. NTN, just because of the clout of the people behind it and the companies, there's definitely some thing that you cannot ignore. That's what I would say, but it's still very early days. I mean, you're still looking at another 2-3 years before things, will change. There will be additional things that prop up, so we just have to keep watching.
FR3. So is there anything more to be done other than propagation modeling in FR3 for research? It's just a spectrum. It feels like
It's just a spectrum, yes, and not at this time. No, that's why there are many companies that are starting to go towards that very quickly, and even that'll start getting commercialized fairly soon, from what we see.
Other questions? Maybe I have a question about data sets. So there is a lot of discussion about the availability of data sets, and Sergey mentioned that they may be artifacts about the data. We actually had in AirPower, there will be a data set session in the afternoon. We have data sets that we thought we had like the telemetry data, but they weren't there. We had to go back like to measurements 2 years ago and try to extract them from the drone. So where do you see AirPower, for example, contributing in data sets? What kind of data sets can be helpful? Or maybe also asking to the audience, do you have any interest in the particular sets of data sets that can help in your research? It's a very general, broad question, but I hope so.
Question. I think at least radar and communication coexistence type of data sets, where we might have like different radar nodes and really observe their effects on actual AirPower receiver systems, base stations data, for example. Those will be helpful to show results in terms of being able to detect different type of radar signals, understand their modulations, parameters, and be able to coexist with them. I think that those type of data would be helpful if we can do that in AirPower, definitely. Any other suggestions?
So I was just going to say that maybe not so much data sets, but having ways of getting kind of like real-time ground truth when conducting an experiment would be helpful. In my work, I'm kind of increasingly going towards the super lazy alternative of having no data prior to deploying a system, just because I've seen that you can still collect a lot of, batch pre-trained data and have such significant mismatches that it's causing me to really question, is it really worth my time and money to even collect the data? And so I'm kind of moving away from even doing fine-tuning of models with real data prior to deployment, and moving more towards how can I do the best type of pre-training using physics-based models and simulations, and then doing online learning once I've deployed. But in order to do online learning, now you have a whole bunch of other questions, because there's also nefarious actors out there. There's people who might be trying to spoof and jam your signal. You might have incorrect measurements. So how can you get some kind of ground truth so that you maybe get like a correction signal or real-time fine-tuning for robust online learning? That might prove to be, I'm thinking, maybe like a more effective way of dealing with the data challenge than collecting a lot of different data up in advance that might not really help you.
Yeah, no, I think it's the no data is an interesting thought process, right? I think the challenge is, again, whatever data you collect, you're going to be challenged as to why you think that is reflective of what you have. And today, if you know how it operates in a real network, they do drive testing. They actually run routes, and it's so primitive if you look at it, because depending on when you drive, and they drive at different times, of course, and then they try to extrapolate what the traffic pattern is going to be in that city at different times, and then they base their network planning to a large extent on something like that. It's been done for ages. It's very primitive. So there is definitely better alternatives. Clearly, there is a need for intelligent data creation. It's not just taking it from one source, but I think you need multiple sources. Also, how you curate that data once you have some seed. It doesn't have to be whatever, but can you be creative in saying, look, I got obstacles here. This is going to be downtown. This is the map, and I'm going to really draw something and see how the routes are, and extract data out of that or create data out of that pattern. I think if we can create tools like that, and that's what we're looking at, it could be very valuable in generating more realistic data, because the conditions you can never foresee. Like you said, there could be jammers, there could be lots of different things that come into play. Buildings and risk comes into play as well. Reflective surfaces. How do you really model it? So you can go really crazy, but I think what I also was learning recently was you only need 10% real data, and 90% can be approximated, and you're still going to get close enough to what you need. That's an interesting one. I mean, because you're always chasing that holy grail of, let me get all operational data. Impossible. You can get it. So how do you get close enough to that? And the 10% was interesting. It's close enough to your no data, but there's a little bit of real data, and then you can approximate the rest. So if there are thoughts about how you can do that, I think that's going to be very important.
What I'm saying is a very good opportunity for with the ARPA. We have a lot of data sets collected. With that, using that, we can create a lot more data sets.
Any last burning questions? Otherwise, we can go to a short coffee break. Yeah. So, all right, let's thank to the speakers again for the great panel. So we'll have maybe come back at 10:40. We have 15 minutes break for the coffee, and we'll continue with the